This lecture is on rotating conics and systems of conics and finding the solutions of systems of conics. So first with rotation, it's actually convenient to write a conic not in its form in terms of the type of conic section, but in this general form with these coefficients a through f. Note we have this bxy term. The xy term is what is involved with the rotation. And if we're going to graph a conic, we need to somehow deal with that and get rid of it and figure out what it means so that we can graph it in ways that we've done before. Here's a rather detailed procedure, and then I'll go into a little bit more with it. First, we've got to find this angle theta, which is the angle of rotation that this conic will go through. Then we plug our angle that we find into some substitution equations I'll show in a moment. We get our equation in terms of now not x and y, but x prime and y prime. Once we've simplified this equation to a standard form, there should be no x prime, y prime, xy term left, so that we're able to graph it as we've learned how to do before. Then we make some axes, put on new axes at the angle theta, and we graph our conic on our new axes. So we find our angle of rotation, we plug it into some equations, which we then plug into our conic equation to remove the xy term. We make axes, we rotate the axes, we graph our conic on our new axes. So a little bit more detail about some of those steps. To find the angle of rotation, the angle of rotation is that angle such that cotan of 2 theta, where theta is the angle, is a minus c divided by b, where a, b, and c are these coefficients on your x squared, your xy, and your y squared terms. Once you've found theta, you plug it into this equation. X is x prime cosine theta minus y prime sine theta, and this one, y equals x prime sine theta plus y prime cosine theta. A proof involving polar coordinates is in the textbook that I will not cover in this lecture. As far as an example now, we have this basic rotated conic. It's a rectangular hyperbola. Xy minus 1 equals 0. So there's no x squared term, there's no y squared term, so a is 0, c is 0, and b is 1. So you do cotan of 2 theta is 0 minus 0 divided by 1, which is 0. Cotangent is 0 at pi over 2, so 2 theta is pi over 2, so theta is pi over 4. We have our theta value. We plug it into our equations for x and y to get now x prime and y prime. So we plug it in here and here. We get x is the same as x prime minus y prime over rad 2. Y becomes x prime plus y prime over rad 2. We take these equations for x and y that we have here, and we plug them into the original equation, xy minus 1 equals 0. So that's what we're doing down here. We plug them in here. That's what's in blue. It's these substitutions. Note when we simplify it, there's no x prime, y prime. Now we rewrite it, and we can see in standard form it's a hyperbola centered at 0, 0, going out rad 2 in each direction. So we draw our x and y axes. Then we draw our x prime and y prime axes at an angle of 45 degrees. And we draw a hyperbola the way we would have, just sort of by turning your head. As far as choosing a different angle, there's cotan of 2 theta is equal to 0 in many different places. So there's other places we could have chosen that would have worked. But if we chosen a different theta value, when we plugged it into our substitution equations, it would have changed the equation as well. And either way, we're going to end up with this graph. Okay. Now for an ellipse, here we have this equation. Our a is 7, our b is negative 6 rad 3, our c is 13. You plug it into your equation to find theta. Cotan 2 theta is 1 over rad 3. Unit into theta is pi over 6. You've got to know your unit circle for that. Plug in pi over 6 into your substitution equations. We do that. We simplify them. We plug them into our original equation. It's very heavy on the algebra here. A lot of simplifications to do. We get all the way down to here, an ellipse centered at 0, 0, with a semi-major axis of 2, semi-minor axis of 1. So you draw your axes, x and y, then you draw your x prime and y prime, trying to put them at an angle of 30 degrees, which is pi over 6. And then on those axes, you go up 1, down 1, left 2, right 2, and you draw your ellipse. Okay. Other ways to just graph these things in a more, in a quicker fashion, really. One way to do it is to solve it as a quadratic. Let's say we have this equation here. Now, this is not as rigorous, and so we will look at this as well. What we can do is, because our calculators can do y equals, we can treat this as a quadratic equation in y. And so I rewrite it as 7y squared plus 50xy plus 32x squared minus 52. So it's a quadratic equation in y where my a would be 7, little a. This is not the big A, B, C DEF we were shown before, but little a for a quadratic equation, a is 7. My b is 50x because that's the coefficient on y, and my c is this whole quantity, 32x squared minus 52. So I plug this into my quadratic equation, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And what I can do in my calculator then is I'll put the square root of the discriminant over here, and I'll do negative 50x plus that over 14, then negative 50x minus that over 14, and we go ahead and graph it, and we're going to get a graph for the hyperbola. Now, of course, it's not going to be as exact as doing this by hand and figuring out things like asymptotes and rotational angles, but it is a way to get a graph. So here it comes. So that's one wing of it, and sometimes depending on the way your conic you're doing, it comes out in different ways as far as which piece will graph which part of the which equation will graph which part of the graph. So that's one way to do it. There's actually an even easier way, and to do that we can just go over to Wolfram Alpha. So go over to Wolfram Alpha and you just type in plot 32x squared plus 50xy plus 7y squared equals 52, and there you go. There's your hyperbola. Now I knew that this was a hyperbola because I've done the problem before, but how do you know these are hyperbolas in some faster fashion? And there is a way to do that. Skip this example. Classification of conics by this discriminant. So now we're not talking about the discriminant I was talking about a moment ago. Now we're back to the capitals, A, B, C, D, E, F. So it turns out that for b squared minus 4ac, it's interesting that it's the same discriminant you learn in quadratic equations. If that's less than 0, it's an ellipse or a circle. If it's equal to 0, you have a parabola. If it's greater than 0, you have a hyperbola. So that's a quick way of telling at least what kind of conic you have. As far as whether it's an ellipse or a circle, well, you can't have any b term and have a circle. Circles, well, they're invariant under rotation, so you wouldn't have any b term there. And then an example of this type of problem would be over here. Our A is 36, capital A is 36, capital B is negative 60, capital C is 25. B squared minus 4AC is equal to 0. So therefore we know this is going to be a parabola. Okay, so that's rotations of conics. Now we're going to take a look at systems of conics. Systems of quadratic equations. And the thing about systems of quadratic equations is if you have things, it's not like two lines when if they're going to intersect, it's just going to be in the one point if they're two different lines. You can have anywhere from 0 intersections to 4 intersections. If you had a circle that went over both wings of this hyperbola, you're going to have 4 intersections, and you can have 3 if it just skips off one side, so it gets a little bit more complicated. The idea here with this equation of a circle and this equation of hyperbola is we want to eliminate or substitute in some way, the same way you would have done earlier with just lines, but it's a more complicated prospect, obviously. And so one way to do this is by adding the two equations, and when you add the two equations, you're just left with a quadratic in x. You factor it and get x is 3 and x is 5. Plugging back in 3 and 5 into these equations, you get different values for y, and so you get these solutions. Here we have an ellipse and a parabola. Here's the ellipse, here's the parabola. This one is done by substitution. We solve the bottom equation for y. Y is 1 minus 1/4 x squared. Plug it into the top equation. Lots of algebra. We get this quartic, which we then can factor and get 0 and 2. This one doesn't have real solutions. You take x is 0 and x is 2, plugging them back into this equation here, and you get a couple values for y, 0, 1, and 2, 0. So one more example over here. So x squared plus y squared is minus 25 is 0. That's a circle centered at the origin of radius 5. 9x minus 4y squared equals 0. That's a hyperbola, which I believe opens to the right. So what I'm going to do is I will multiply this equation by 4, because then I can add these two and cancel out y's. There's other ways to do this problem too, but this way works. So we add the two equations, and now we have a quadratic in x, which I can factor. I'll get two values for x, negative 25/4 and 4. So first, if I plug negative 25/4 back into this equation, because it is a simpler one, I have a quadratic equation in y. And this is actually going to give me no solutions. So this doesn't help me at all, or doesn't give me any, at least. It does help me. Then if I plug in x equals 4 into this equation here, 36 minus 4y squared equals 0. So y is plus or minus 3. So overall, my solutions are 4 plus or minus 3.